That was a review of some fundamentals. If we use this as our first example, y equals 3 raised to the x, and we have a table of values here, we could plot this table of values to see what the pattern looks like as a graph. And then we can start talking about domain and range and potentially asymptotes and intercepts. All those things we've been learning about graphs. So if we take this table of values and plot it, and the base happens to be a 3 in this example, a base of 3. And so if I look at the negative numbers here first, over to the left at -2, this value at -2 is 1/9, so it's a very tiny value, 1/9. And if I'm at -1, it's 1/3, 3 times as much. 3 times as much, notice. Everybody hear that? I moved over in the domain one spot, and the value jumped by a multiple of 3. Okay, let's keep going. If I move to 0 for x now, and I previously was at a 1/3 value, 1/3 times 3 is, what's 1/3 of, or I'm sorry, what's 3 times 1/3? 1. So as I move to the right here, as I move to the right through the domain, I'm observing a multiple of 3. A multiple of 3 in the heights. Every time I click over 1, I'm jumping a multiple of 3 on the previous height. Keep plotting. So I'm at 1 here, and that's an important point. And then when I go to the next spot over at 1, positive 1 now, I'm going to be up at a value of 3. Okay, and if I go over 1 more to 2, I'm going to be 3 times 3. 3 times 3 gets me to 9. I'm going to be almost off the, well, probably off the board there. Okay. Oh, what about numbers in between these whole number or these integers here in the domain? What about numbers in between? Look at this. If I come right in here at 1/2, at 1/2 for the exponent, 3 to the 1/2 power. What does the 1/2 power mean? It means square root, right? It means square root of 3. That's an irrational number. It's a decimal that never terminates and never repeats itself. Okay, so what we get if we punch that on our calculator is 1 point something. And if you go in here at 1/2 on your graph, you're going to get 1 point something in here. And think of this, understanding this real clearly. What if I went to say 1/4 or 1/3? How about 1/3? 3 to the 1/3 power. That means cube root of 3, which is even closer in value to 1. At 1/3 here, it's going to be even closer to this height 1 right there. And if you do that for a whole lot of points, or let your graphing calculator do it, you will get a nice example of an exponential function. So there is the graph of y equals 3 to the x. Feel good? This point is a very important point, this y-intercept. This is called a knee, or I also will call it occasionally a key kind of a point. That value right there. That's one. You know how with your parabolas and your radicals and your other fundamental library functions, you have to keep track of not just maybe a vertex or something. You want to keep track of a couple other points to help you plotting with transforms, right? When you shift and stretch and squeeze. Okay, so what you want to keep track of on these exponentials is the knee point, the y-intercept, on what happens to it, and you also probably want to keep track of what happens when the fundamental function in your library is at a value of 1. It's going to be how tall? It's at 1, it's going to be the height of the base, isn't it? That's going to be the base height. It'll be the height of the base, right, at 1. And then if you move over another to 2, what happens to the base? What do you do to the base? You multiply it by the base. See, this is 3 to the first. Over here, when you're over at 2 now, at 2, it's going to be 3 to the second. And when you move to 3, it's going to be 3 to the third, 3 to the fourth. So the way I like to explain this is exponentials grow as a multiple of their base. Try to remember that. You can quote me on that, okay? Exponentials grow as a multiple of their base. Exponentials grow as a multiple of their base. Let's do 2 more things before we get practical with it. Question? Yes?
Do we care that as x equals negative infinity, y is approaching 0?
No. As a matter of fact, I'm glad you asked that. I forgot your name. Alyssa, yeah. What Alyssa's observing here is as you head to the left, this thing never hits the x-axis, does it? Never hits this x-axis. What if you're at minus 20? Way off to the left at minus 20.
We're really close.
At minus 20, the value would be 3 to the minus 20, which is 1 over 3 to the 20th power. That is a microscopic number, folks. Microscopic. 1 divided by that huge, huge number. Okay? And so it never actually hits 0 out here to the left. So, Alyssa asked the question, what happens off here to the left? It never actually hits 0, you said, and that's true. And so what that tells you is that your domain, how far to the left could you go? You could keep going, couldn't you? How far to the right? Keep going. So the domain of your exponential functions in their fundamental form is all real numbers. Domain is all real numbers. The range, however, water level, right, rising, can never be below 0 or 0, can it? So it has to be above 0 and goes on up forever. Domain and range. Those are important. The y-intercept, this knee or key point, is important. And the point at x equals 1 on exponential functions is typically very important. Okay, not too much to remember, not too tough if you understand the fundamentals. All right, any other questions? Okay, next step. How does how does the graph of using one base compare to a graph using some other base? In other words, if you see one versus another, how do they behave? And let me go ahead and I'll try to leave that one up there, but I want to draw another one for you so it'll be kind of clear. So let's see, I just did 3 to the x. So let's say 3 to the x looks like this. Okay, so let's say it looks like that. And if you could come in a little closer to the camera, that'd be helpful. Okay, now, and here's your key point. Let's now imagine a base instead of 3, let's say it's a base of 10. Base of 10. It's going to go up faster, Melissa says. Other people agree? Okay, it's going to go up faster. In other words, when you're at 1, it's going to be up at the basis value, isn't it? It's going to be clear up at 10 instead of at 3. It's going to be clear up here at 10. And when you're over at 2, instead of being at 9, it's going to be up at 100. Wow. Get excited about that. That's going up like a rocket. Now, how about when you pass the knee and come to the left? When you're at -1 on the 3 to the x graph, that's at 1/3. Maybe you could zoom in a little more, would be nice. 1/3 there. And then on the other graph, on the 10 to the x graph, it's going to be at 1/10. Wow. This thing comes down, and that knee acts as almost a crossover point. Actually, it does act as a crossover point, doesn't it? Same domain and same range, but you see dramatically different character in the sense of how fast it rises here and how quick it comes down and settles out towards the asymptote here. This has a horizontal asymptote, y equals 0. Let's do two other important bases. Yes, Alyssa?
Can we find the asymptote using the equation, or is it just where it hits the y-axis?
Good question. Here's the deal with asymptotes, and we've done this with rational functions in particular. And I've gotten in the habit with you of showing it this way if I'm going off to the left. If I'm letting x go towards -infinity, then look at what happens to our function, say 3 to the x, as you let that go towards -infinity. You're coming off to the left, folks, and you're looking at what happens to the y value. It starts behaving in the limit as this exponent here becomes hugely negative, right? And based on what we talked about a little while ago with negative exponents, isn't that the same as 1 over 3 to a huge number exponent? Which is 3 to 1 over infinity. 1 over a huge number. What's 1 over a huge number? 0.
Slightly positive 0.
Yeah, slightly positive. Excellent. So that thing's heading towards 0 from the positive side, and we saw that in our rational functions frequently. The further out here you go to the left, it's being driven towards 0 from the positive side. Very nice. If you folks are understanding these kind of trends, these kind of limit things that I've talked about with rational functions and now exponentials, you're going to be in really good shape when you get into calculus. And math is just a stepping stone process. You build a platform and then you step onto the next platform. It won't get any more challenging probably for most of you if you learn your fundamentals and just step from one to the next. You can keep on rolling with this stuff. Okay, any other questions? All right, let's do a different base. Let's do a base of 2. Let's do a base of 2. If I do a base of 2, it's going to be below this 3 to the x graph off on the right here, isn't it? When I'm at 1, it's going to be up at 2 instead of at 3. It'll be at 2. And when I'm at 2, it'll be at 4 instead of 9. Right? So it's coming over like that, 2 to the x. And what happens at the knee? It's going to cross over those other graphs. And it's going to be actually higher as it heads on out here to the left. Nevertheless, same domain, same range, just a somewhat different, flatter character. I've got 2 more to lay on here, and then it's going to be too jumbled for us to use it anymore. Let's say its base is 1.05. 1.05. Where's that graph sit?
Almost flat.
Almost flat, thank you. So at 1, it's going to be 1.05. At 2, it's going to be 1.05 times 1.05, which is still pretty close to 1, right? Okay, so it's going to be pretty close to, like Melissa said, pretty close to a flat line looking graph. Very slow growth. And then similarly crosses over at the knee, heading off to the left. And what if this base degenerated, folks, from big numbers like 10 to 3 to 2 to 1.05 to 1? 1 to the x. Yeah, that's always 1, isn't it? For all real numbers. That's just a straight horizontal line like y equals 1. There it goes. So if you understand what we just did here, you have this whole family of exponential functions with positive bases bigger than 1 looking like this. Okay? I've got one more base bigger than 1 to throw in here. Anybody know what that base is? It's called e. It's a funny number. It's a very, very important number, though, that has very special properties that after this course, you will learn about it. So you're so excited you can't wait to take your next math course. Okay. It happens to be in between 2 and 3. It's called little e, and it's built into your calculator, and it's built into all the math books from this level on. E to the x happens to be a number, this is a good one for you to memorize, 2.718, keeps on going, never terminates, never repeats. It's similar to pi, being one of these irrational numbers, raised to the x. And so it's going to sit, look at the base, folks, it's going to sit between these two graphs. So there's your e to the x graph. Don't forget that one. And again, it's going to cross over at the knee and sit between the 3 to the x and 2 to the x graphs over here. Jennifer?
Will it ever cross the y line?
Will it ever cross this line?
No, the y, the
Oh.
horizontal.
Oh, you mean the, oh.
When you're putting bases on, I mean, no matter what base is on there, up to 1,000 on a base, will
Yeah.
it ever cross the y line?
Will it ever cross
Back over.
this line?
Yes.
Oh yeah. Where does it cross?
Not at the knee, just
Oh.
when you go higher, not when you get to the negative exponents.
Just gonna follow that wall straight up.
Is it just going to go straight up the line?
Straight
When
up.
you reach-
I'm sorry, I'm misunderstanding what you're.
Do 100 times at 100 at a base of 10. Will it ever cross the horizontal line going back over?
No.
That's what I'm asking.
This horizontal line.
That's vertical line, isn't it?
No, this is
Vertical.
horizontal.
The wind goes all real numbers, so it's always going to go up.
Yeah,
No trust.
keeps going
Yeah.
up. Keeps going up. Always gets steeper and steeper the further
But
up
never
you go.
curves back around.
Oh no, can't ever. It wouldn't be a function. Is that what you're getting at?
Yeah.
No. Okay, think about that. Good point. Will it ever roll back over itself like this to where it would have 2 or more y values? No. Are there? Think of any of these bases here. Think of putting an x value in. How many y values do you get if you put a number in? You only get 1, don't you? You only get 1 y value. So it's never going to get so steep. You might think it would. You ever blow up a balloon and let it go? You know, it might just take off and zip back over you or something. Wouldn't be a function as far as its flight path goes. So it will never roll back over itself. It will just always continue to get steeper. Okay. This graph's getting kind of messy, but I could do one more thing with it. Notice I haven't drawn anything over here yet. What could I do? These are f of x's, right? Think of these as f of x's. They're very nice looking functions, aren't they? Okay. Now, what happens if I go into any one of those and I replace this x with a negative x? What does that do to the graph? Very good, Jennifer. It's going to turn it, if you replace the exponent here with a negative, it's going to turn it around the y-axis and kick it over here, isn't it? So look at this. If I write y equals 2 to the negative x, That should be the exact same graph as 2 to the x, except rolled over the y-axis by our transformations. And so it's a graph that's going to look like this, comes down through here. That is called a decay exponential. Obvious that it's decaying in value as you move through the domain. Everybody comfortable with that? If you ever replace x with minus x on a function, it turns it around the y-axis. That's something we studied quite a while ago. Turns it around the y-axis. So any of these graphs here with a negative x on them, on their exponents, is just going to turn them over the y-axis. Look at the math. Look at the exponent rules here. Isn't this the same as 2 to the negative 1 raised to the x? But what's 2 to the negative 1? 1/2. This is exciting. You don't look very excited. Look at, we talked about bases here, bigger than 1, didn't we? Bigger than 1 are growth exponentials. Over here, the base is still positive. And I said earlier, the base has to be positive. But these are numbers that just happen to be smaller than 1. And so if the base becomes less than 1, has to stay positive, less than 1, they're just going to be decay exponentials. Okay, very, very handy, very important. Okay, if you absorbed most of what I've just said, we're now ready to do something real. Most of us are somewhat interested in money. Okay, to buy food, to buy Apple iPods, whatever it might be, okay? That sort of stuff. There'll be a homework quiz.